Hello everyone. In this video we are going to talk about the morphological operators, the operators that you perform on binary images, zeros and ones. And they are extremely important when it comes to higher level tasks in image processing and computer visions. Probably what you have seen them so far used for is masks, right? But they have a lot more applications and like object tracking and recognition and so on. And if you want to have some useful masks, useful labels or anything like that, the matter of fact is the simple act of thresholding and binarizing this way that I showed you in previous videos of mine is not going to create perfect masks, nice masks or labels or binary images, because it's hardly ever that you see in real images, not synthetic ones that you make with software, that you have a homogeneous region in terms of light intensity or color or anything like that. And the values in the pixels do vary from place to place. So when you get a mask or a label, you typically see holes in it. You see there are areas that are disjoint while you expect them to be connected together and so on, right? So for example here, if I show you this case, so here the picture is this one. Let me show you. So I'm reading this set of spools, this picture, a real picture, and all I want to do is to find, basically create a binary image where it's 1 for the red spool, everywhere else is 0. And the simplest thing you can imagine is, hey, I find out what ranges of red, green, and blue are these pixels, and then I try to threshold the red, green, and blue values of pixels to only within the range of those pixels, and then I get a binary image. So you can click on this data tip, you go here, and then you move this using your arrows, you move this cursor all over the image and try to look at these red, green, and blue values. So you see they have a high red value and a low green and low blue. But look, when you move to some other areas, look at that. Here the blue is 30, the green is 25, right? 29, 31, 39, right? You see both of them are 39. While for most of the other areas, if you look at these, it's below 20. While on the right hand side, you approach close to 40. You see right now, you even pass 40 on the blue, 35 for the green. And now look, the green and the blue are even bigger. So it is really hard to come up with a single threshold for red, green, and blue. And you see here, for example, I apply some filter. I say anywhere where red is bigger than 180, blue is less than 30, green is less than 30, blue is less than 60. So I create this binary image using the logical operators and here. And then if I show that image to you, that definitely does not have all of the red spool, as you can see here, side by side with the original image. You see, it only captures a portion of the red spool. It could very well filter the rest of the spools, which is good, but clearly you see that it eliminated a bunch of the pixels that you want. So now it is time for me to do something on it, because clearly you see there are so many pixels missing, and it's not even one single region, it's separate regions. So is there anything I can do on this to improve it and get it closer to the shape of the actual spool? That's morphological operations, right? Working on binary images. So what do we have here? So there are a bunch of morphological operators that you can perform on images, and here we focus on the powerful ones in MATLAB, image processing toolbox. The first one we can talk about dilation and erosion. Dilation is basically thickening the white blobs, and you hear me saying the word blob. Blob is basically a connected set of white pixels, and erosion is to make them thinner. Okay, now how would you do that? To do that, we need something called structuring element. Okay, so let me make this bold font for you. So a structuring element is basically what you use to combine it with or move it along the pixels, mostly the boundaries of your binary blob, and then extend or thicken it. For example, let's say the binary blob you have is this blue square, and the structuring element you have is a disk, where inside the disk it's all 1, outside the disk it's all 0. So how can I use that disk along with the original blue square to get what? A thickened version of the square, which here you can see it's this bigger square with rounded corners. The color is cyan. And how can I do that? Well, the dilation, which you show dilation of blob A by structuring element B, is shown with A and then this symbol, which is a circle with a plus inside, B, this symbol, if you see it in image processing, that's dilation. So dilation of A and B is what? If we read it in plain English first, it's all of the pixels where the translated or reflected structuring element B still overlaps with at least some portion of A, really. So what does it mean? It means if I put the disk here, if I move it or reflect it, which is the mirror image of itself, anywhere in the image such that disk has some overlap with a portion of my A. So here you see at this point, this area is the overlap, is the intersection. So I can put the origin there, and then that disk is going to cover this whole area. So now any pixel that is covered in that area, I'm going to change it to 1, which is the same as the ones inside the disk. So if this area that was cyan, and let me use a different color, that was black now, correct? It was black originally. Now, because the disk can go there and still have overlap with the original blue square, now I'm gonna turn all of that black area into what? I'm gonna make them all 1, which makes them white. And then I move this origin all over the place and try to what? Basically get these white pixels, or these pixels with 1, to cover as much area as possible inside the black area. Okay, so this is called what? This is called the dilation, and mathematically you can see that those pixels for which the reflected or translated version of the structuring elements intersection with the original blob has something. It's not equal to the empty set. Okay, so this is the dilation, and as I said, for it you need a structuring element. How would you create a structuring element in MATLAB? There is the command called strel, structuring element. And structuring elements in MATLAB, they have different shapes. It's not just a disk. You have the disk, you have a diamond, inside of it 1, outside of it 0. You have octagon, you have line, you have rectangle, you have square, and you can even come up with your arbitrary shapes of ones and zeros. Okay, so I'll show you in the code, but this is how dilation works. Now, the good things about dilation is commutative, it's associative, and it's shift invariant. What does commutative mean? It means like A plus B, of course this kind of plus, A dilated by B is the same as B dilated by A. So it doesn't matter which one you use first, which one you use second. Or it's associative, right? So A dilated by B, which is dilated by C itself, is equal to first A and B dilation, then dilate the result of that with C. Okay, so that's associative property, and then shift in, which is basically the result does not depend on the location of A. So if A is that square here in the image, and I use the disk, I get the same result as if the square was here and I applied the disk. The result of both is going to be that thickened square, basically. Of course, the location of that is going to be different, but the size and the properties of the result are the same. Okay, so it has some good properties. Now here you can see I have applied this dilation to the result of that red spool, right? And for it, I used a line instead of a disk. I use a line. Now when you use a line, when you use a disk, you have to provide the radius of the disk. When you use a line, you have to provide the length of the line and the angle of the line. Okay? So what I'm doing here, I'm using a horizontal line. Basically, that's what it is, a horizontal line. Inside of it 1, outside of it 0. And then I put it all over these pixels and perform the what? The dilation. What does it do? It makes all of these disjoint pixels that you see here, 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 it kind of connects them together, thicken them, so that's what you can see here, right? They're all connected now. The other thing I did in the code to generate this right image, actually, I used another line as well as the horizontal one. In the next step, I'll show you right now in the code, I used SE2. This time, I used str elements of a line again, but this time I used, let's say, 5 pixels, and the angle I changed it to 90 degrees. So now I have this kind of element. What does this one do? It makes the elements on the left and right to be welded together or joined together. So I would get this 2 areas thicker, but still I have this gap in the middle. But once I use that vertical element, you see now the gap is also what? Taken care of. So now I have a single connected element using 2 STRLs. Could I have used a disk instead of both of these lines? Yes, I could. Okay, but the disk does not produce as accurate edges as the STRL line does. Okay, it kind of rounds the edges, but if the exact perfect shape is not of a concern, you just want these disjoint areas to be welded together and become one single region. Instead of those, you can use what? You can use your disk or octagon or any other shape. So if I go to my code, I have written this big demo code, which I will share for you. You can find the download link under the video description. So here I read the image, you can see. And then here in the next section, as I said, I binarize it, and you see here I use 2 lines as a structuring element, and I dilate it in 2 separate steps, and then I show you the final result. So let's go ahead and run this. There we go. So this is the final image, as I showed you. This is what? The original threshold result, thresholding, and this is the original image. Good. Still, this is not perfect, but much better than the original one. So this is like post-processing binary images that are not good. You post-process them using morphological operators to make them better. Okay? Now you might say, well, how did you know what kind of element to use, what length, what angle? Well, I didn't. I still don't. I'm just basically trying different structuring elements and see which one gives me the better results. Definitely these two are not going to give me the best result. I can definitely do better than that. Here the goal is to just show you how they work. So is there any way that I can know ahead of time which structuring element with which parameters will give me the best blob? No. You have to what? You have to tune it, fine tune it, right? So first you have to come up down to which shape is the best. Then from different parameters that shape can take, which one. So it is an optimization really, if you really want to do it perfectly mathematically. If not, really, you have to fine tune it. And as I told you in the first video of computer vision, every computer vision is application dependent. The numbers you use, the parameters, the everything that you use depend on what you want to do. Okay, so there is no one fit all solution here. Okay, there is another one that I mentioned, erosion, which is the opposite of dilation, and that makes the object boundaries thinner, and it is defined by a minus b, where minus is inside the circle, and the definition of that is this: the set of all structuring element origin locations for which the translated b has no overlap with the complement of a, or background of A. What does background of A means? Means if this is A, background of A means make every black pixel white and every white pixel black, complement, 1 minus the image, 1 minus the binary image. Okay, so it says all of the pixels such that the translated B, as you can see here, intersection with A complement is not equal to 0. Okay, so for that case, if I come back to this shape here, right, if this is my big image and this is the blue square, so now I focus on what? On the A complement, which are all the areas I'm hatching. I put my B center such that it does not have what? An empty intersection. So if I put it here, the disk, it goes like this. Does it have intersection, this B right now with A complement? Yes, it's this area. So I can put it there. Good? And when I put it there, what do I do? Instead of last time when I dilated, any area that the disk covered, I made it what? I made it 1. This time I do the opposite. I make it 0. So what's going to happen? This area that I'm painting in green, where B and A have overlap, instead of 1, I make this area 0. So when you perform that, your boundary is going to be this one now. It's going to be thinner than the original one. So that's erosion. Okay? So hopefully erosion and dilation are clear. In MATLAB, the commands are IMDilate and IMErode. Okay, here I showed you dilate. I can show you erode as well. Of course, for the sake of this already thin boundaries or thin parts of the spool, if you do erode, it's gonna even make it worse. So what does it do if you erode it? It eliminates all of these small pixels, isolated pixels. It definitely first get rid of them, all of this, and then it goes over these thinner ones, tries to eliminate those as well. So if you do that, you probably get something like this. Just these two areas in red. Anywhere else will be taken care of, converted to 0. Okay, so that's what? Erosion and dilation. So dilation is good to create thicker stuff and join disjoint areas together. Erosion is the opposite, to get rid of small areas. Okay, so hopefully that is clear. So what else do we have on morphological operators? The next set of commands that you can see in MATLAB are opening and closing. So I am open, which is A dot B, and this dot is like a little bit thicker, actually, it's like this. This closing of A by B, again, B is a structuring element and A is your original binary image, is the dilation followed by erosion. So you can see here, A is dilated by B and then eroded by B. That's closing. So closing is dilation followed by erosion. Opening is the exact opposite. Opening is erosion followed by dilation. So it's going to be like A minus B and then plus B. This is opening, which if you want to show it with a symbol, the symbol is again A and B, and it's a circle, but instead of a filled circle, it's a hollow circle like this. Okay, so this is opening. And this is closing. Good. Now what do they do? Of course, opening first removes the small fragments and then tries to connect them together. The closing first fills the gaps and then tries to erode the extra boundaries. And you might want to ask, you would ask, why should I do both of them at the same time? Why shouldn't I just dilate or just erode? Why should I combine? Well, the combination is to keep the size of the boundaries of your blob the same. Because clearly, dilation will make your boundaries thicker than they are. And the erosion will make them thinner. So if you apply them together, the size of your blob is not going to change overall. But what's the effect? Well, the effect is this. If you have this guy and first what? You dilate, so you make all of these disjoint areas to connect and be a little bit thicker. But now that they are connected, when you apply erosion afterwards, what's going to happen? They are not going to go away because now they are all connected as one blob. So now it goes back to whatever it was. But guess what? This time it kept all of these areas. So you get this. Okay, so this is what? This is a closing. You want to keep the isolated pixels because you believe they should be kept, right? They should be kept. So you first dilate to keep them and then erode to get rid of the extra boundaries that dilation brought with it. In erosion, you do the opposite. You first get rid of these extra things, right? And make it thinner and then make it thicker again. So at the end of opening, you will get this. Okay? So it depends on what you want to do. But why do we do both of them at the same time? As I told you, the only reason is to see whether you want to keep the isolated areas and fill the gaps, or no, you want to get rid of them. So here, if I show you a result, here is some original image that you have these kind of circles with some gaps in them. If you do closing, what's going to happen? Well, here, as you can see, all of these gaps that you had are what? Are now preserved. And if you look at the boundaries, they are a little bit thicker than they used to be. Compare here against here. And you clearly see the boundaries are what? Are thickened a little bit, but not too much. So the idea that closing and opening is going to give you perfectly the original edges back, it's not right. It tries to preserve as much as it can and give back the original size as much as it can. And you can see that here. If you look at this area in red, that's the same as here. Okay, so it definitely tries to preserve some of the original boundaries. You can see them here, here, and so on. But is it going to be all over the image? No. In some areas, like inside this red circle, you see some boundaries might shift, but it's not significant. Because after dilation, you did erosion. So a lot of the boundaries are preserved, except for, as I said, very sharp corners like this. They will expand a little bit. But the good thing is, look here, that hole in green is now gone. Here it's gone. These two are all gone. Okay, so it preserves and unifies the area. On the other hand, look at here. This is a fingerprint, okay, a portion of a fingerprint which has a lot of extra isolated pixels that you don't want to have for, let's say, fingerprint recognition. So you do an opening. What does opening do? It gets rid of all of those small pixels. And what, if you look at the size of the, or the thickness of the lines between these two images, they are almost the same because opening is erosion followed by dilation. But what is it that you're missing? The missing part are all of these fracture lines that you have now. If you look along this, there was no fracture line. But now if you look at the same thing, there is one here, there is one here. There is one here. Okay, or if you look at this bottom one again, look, there is no fracture line, but if you look here, there is one here, there is one here, there are two partial ones here, maybe there is one here if you zoom more. So you get all of these fracture lines. So if you want now to improve this and get rid of all of those fracture lines, you can do a closing after opening, and here you do what? You try to, as you can see now, get rid of all of those fracture lines. Okay, so closing is covering for fracture lines without thickening the image significantly. Opening is getting rid of the small pixels without making the image much thinner or much thicker significantly. Okay, so in MATLAB, the commands are IM_open and IM_close here. So here, the same image that I had for the spool, I used a disk of radius 3, and I show you both the open and the close version of the image. So let me run this section for you. Okay, so this is the close image, this is the open image, and this is the original binary image. Let me put them side by side so you can see. Okay, so when the image has a lot of small fractures, opening kind of eliminates a lot of them and make your boundaries poor and small. Look at that. I mean, compare this one on the right with this one in the middle. You see, only these major parts are preserved. The size of them are the same, but everything else is taken care of. In closing, you see, first it joined them together and then made the boundaries thinner. So definitely, final suggestion, when you have a lot of small blobs and you want to keep them, you always want to go with closing, never go with opening. Okay, opening is a cleaning job, closing is a unifying job. Okay, so what else do we have? The next thing we have is called labeling connected components. This one in MATLAB, you can use the command bw label, and it finds for you the parts, the blobs in the image that are either 4 connected or 8 connected. Okay? What's the meaning of that? 4 connected means each pixel within that blob, within that connected component, has a connection to at least one of the 4 neighbors. And what are the 4 neighbors? They are the ones immediately to its left or right or above and below. If it has a connection to any of them, then we say that whole part, those pixels, are 4 connected. And then if you put this guy in the center now, you have to look at this one. This one has 1 pixel on the left, it has this guy on the right, it has 1 above and below. So since the one on the right was already a 1, it's good. So now you have to go to the next pixel, to the next pixel, and find any system of pixels that at least the center pixel is connected to one of the 4 major neighbors. Now, another way of connection is called 8 connection. So the neighbors are not just the one on the left, right, above, and below, they are also the diagonal neighbors. Okay, so that is called 8 connected. So if it's only connected to one diagonal neighbor, still they are one single connected component. So 8 connected, when you apply it in comparison to 4, it can allow for your blobs to be bigger in size because they take more neighbors, more neighboring pixels as valid. Okay, so you can have a blob that looks like this and had this extra tail like that, correct? These are all diagonal neighbors of the previous ones, right? Well, if I wanted to do 4 neighbor, probably your blob is only going to be like that. And it would eliminate that tail as belonging to the blob. Okay, so that's the difference between what 4 and 8 connected. The command BW label finds as many isolated blobs that you have, and then gives them a label. So calls this one, for example, L equal 1. If you say L equal BW label of the binary image and the connectivity, which this guy is, as I said, is either 4 or 8. It's called this blob L equal 1. This is L equals 2. You need double equal. I'll show you in MATLAB. Right? This is going to be L equal 3 and so on. So it gives you all of those. Now, can it return empty blobs? Of course it does. It returns as many L's as the number of pixels in the image in one direction. But only the first few of these L's are the ones with non-zero pixels. The rest of them, as you will see, they will all be empty. They will have nothing in them. And that's another thing that you have to do when you're dealing with BW label. So if I want to do that for you here, it's right here, labeling. But before that, I want you to pay attention to something, and that is here, I'm using some threshold and creating a binary blob, a little bit different thresholds than last time. Why? I tell you. So this time, this is the binary image that I'm going to show you. So as you can see, I'm using a little bit different thresholds. And what does it give me? It gives me something different than the original one. If you compare it against this one, not only now this new thresholds will detect the red spool as really red, they also detect a little bit of the orange spool here on the top. Okay, let me show you the original image. So they say, hey, this area fits the threshold, also a portion of the orange will fit that threshold, okay? And that's what you can see here. Good. Now, how many blobs do you see here? If you visually inspect, there are several that are connected. So if I zoom into here, you see they are completely connected except for this single pixel. If you can see, there is one single pixel here. That counts as a single blob of its own. So there is one here, 2 and 3. There are 3 blobs here. One of them is only 1 pixel, I assume. And if you look up here also, there is one here, there is one separate here, there is one here, and there is one with 2 here, plus the giant one. Okay, so there are 4 small blobs, 1 or 2 pixels, and 1 big. That's 5. So that's 5 down there, and I guess as we checked last time, 3 down here. So it's 8. Although you really see 3 giant blobs, but there are 5 small ones too. So when you run this command bw label, the number of non-empty labels are going to be 8 instead of what? Instead of 3. But those are not significant. Those small blobs that I showed you, 1 or 2 pixels, they are insignificant. Can I get rid of them? Yes. That's the second part that I want to talk about before we go over the result of BW label. And this is this part here. Removing small binary objects. And that is the command BW area open, which is a very powerful command. Okay. Oh, there's something going on. Let's see here. BW area open. You pass to it the entire binary image, and then you pass to it a threshold n. What is this n? It tells the computer to get rid of any blob for which the total number of pixels is below n. So when you say n is 20, any blob that has less than 20 pixels total, it will be eliminated from what? From the image. You can see that in this picture too. Here, there are 2 images actually on the top of each other. They are montaged. So here, there is the boundary probably between them or so, right? Or maybe here. So this is the original one on the left. This is the BW area open on the right. I passed some threshold to it, and those letters that do not have too many pixels are eliminated. Which ones? Well, look at that. So if you look, the T is gone, right? And then the R is gone. And again, this T is gone, this R is gone, this R is gone, this R is gone, the T is gone, and the R and the I are gone, T and T. So literally R, I, and T are the letters that do not have as many pixels as the other ones. They are eliminated. And you probably see them here too. So you can eliminate maybe some letters if you don't like them from a binary image like that. Okay, or any blob with few number of pixels that are insignificant. Okay, so that's another very powerful command that does a cleaning job for you, BW area open. So here, before I apply my BW label to this binary image that I just showed you that has those small things, I applied a BW area open. And I said anything less than 20 pixels, get rid of it. Get rid of it. And that makes it a lot cleaner. One other important cleaning job that you can do to make your results a lot better before you apply labeling is filling the holes. Okay, many of these blobs that you have, they have holes in them. They have interior areas that are connected by some pixels, but not by all neighbor pixels, and you clearly can see them here. These are all these holes. Now, let me tell you, this small thing that you see here, this is not a hole because it has a connection to outside zeros. So these are like islands. Okay, holes are the islands that are completely trapped by ones. When you apply the command to fill the holes, it only takes care of them, not these areas that have connection to outside. Okay, how do you do that? There is the command in MATLAB imfill. You pass to it imfill, a binary image, and pass to it the command holes, and it fills them all with holes, and you can see the result right here, that all of these small isolated islands in this one and this one are taken care of. So if I ever want to do a labeling, I do two previous steps. One, I fill the holes, and two, I get rid of insignificant blobs with few number of pixels. So I do imfill holes and I do BW area open, then I do labeling. That's what you see I have done in the code. Right? First I fill the holes that you can see here. Let me show you. Right? You can see them side by side. The holes are filled, the holes are not filled. Still here I have those small areas. So next I do the BW area open. I forgot to run the command first. Here. So now if you put this next to the original one, so this is this one and this one. Good. So having holes, not having holes, but these small ones, and here what? Those small ones are all gone. So I'm only down to 3 clean blobs. So now when I run BW label on this last one, I get something quite meaningful. I'm using 8 connection. I pass the result to the clean image. And if you look at this L in my workspace, let me show you. If I run this for you, if you look at L, it's 342 by 342 double, and my image is 342 by 342. So this L is not going to be just like 1 or 2 or 5 labels. There are going to be tons of labels, but many of them are empty. The blobs for those L's are empty. Only the first few are non-empty. You can use the command find to check whether they are empty or not. Okay, but you clearly see here that only the first 3 are. And how do I get those images? How do I get the single blob? So I say L equal 1. I said the label equals 1. That thing alone gives me an image. Which image? The image of the first blob, as you can see here. Remember, they're all coming from this guy. So it calls one of them L1, one of them L2, one of them L3, and you can see them right here. Okay? Here we go. So you see all of these 3, they have their own label, and they're all coming from this original image. Now they might belong to the same object, or they might belong to what? Separate objects. If you did a good job and you could connect these 2 together using some close or dilate or something, then these 2 are going to be one single blob. So now you will have 2 objects, which is more realistic because this is the red spool, that is what? The orange spool. Okay? So performing these commands properly and using proper thresholds, proper order of commands is very critical in getting final good results. Okay, so I told you about those. There is another very powerful command. It's called bwmorph. And this command can not only do the job of erosion, dilation, closing, opening, filling, and so on that we could do with the previous commands. It can do some extra things that those previous commands could not do. Like what? Like if you pass it this image on the left, it can give you the image on the right, which is like the skin or the perimeter of this image. Okay, so this is converting it into a skin image. Just keep the outside pixels, the edge pixels, and get rid of all the interiors. Okay, so many times you need this kind of thing, which is kind of like an edge map, really. Okay, or another thing that sometimes you might need in higher level vision task is called the skeleton map or something, or a skeletonization. So you convert it into this one. Okay, so especially the skeletonization, the math behind it is a little bit more complicated, and I don't have enough time to go through the math of each and every one of them, but I just wanted to show you this powerful command, bwmorph. So let me show you that. And where is it? Here. So I read that same bubble image, and then I show you this skeleton version and the remove. Remove is to make it the skin image. So if you pass your image and pass the keyword remove, that makes it the skin image. If you pass to it the skeleton image and infinitely thin, which is like just one pixel thick of the edges for the skeleton, that makes it what? The skeleton image. So let me run this section for you. Let's see if I have anything open. Close them for you. And here we go. Okay, so the original image, the skin image, and the skeleton image. Good. So that's a very powerful command. It can do a ton of things. Just go to bwmorph in the help. And if you look for this command, it can bring you what this command can do. So here, okay, this is the help for it, and it can generate all sorts of different beautiful things. It has tons of operations that you can see, right? The bottom hat, the top hat, the bridge, the close, the diagonalization, endpoints, majority, shrink, spur, top hat, and so on. And covering each and every one of them is beyond one single video on morphological operations, so I encourage you to look at them yourself. Okay, the final things I want to talk about binary images are measurements, which are really important. So now when you get some nice blob, some nice binary image, mask, or whatever, many times you want to do some measurements, right? Get something about the size, the shape, the area, the moments, and so on, whether that blob looks like a circle or not, right? What is the bounding box, and so on. Because you want to do object recognition, you want to do object tracking, and so on. So these are definitely needed for many higher level tasks. You want to pinpoint your camera at the centroid of the blob, and as it moves, and let's say that blob comes from your camera looking at an object, and let's say you're subtracting the image of the person from the background, you're doing background subtraction, which I covered in one of my previous videos. So the blob really corresponds to a person. And as the person moves, you want to find the location of the centroid of the person and locate the person, right? So how would you do that? Well, here, there are mathematical formulas for calculating a lot of these properties. And the very powerful command in MATLAB is called region props. So the command is this command, region props. You pass to it the binary image and you ask for some properties, and it gives you the answer as a structure. But if you're wondering how it measured, let's say, the area of a pixel, a blob, how does it do it? Well, the area is simply what? Is simply the number of pixels, right? The number of I, X, and Y that are equal to 1. Correct? If that's 50 pixels of 1 and everything else is 0, then we say A is 50. So here A is not in world units, it is in pixel units. So area, we just say 50 pixels or so. And it's one of the moments of an image. The moment ij of an image is defined as summation over all pixels I and j, or x and y, where the pixel x is raised to power I, the y of the pixel is raised to power j, and then multiplied by the intensity at that pixel. If the image is binary, this I is either 1 or 0. So basically, only those pixels are calculated in the summation that are 1, that are white. The black pixels in the background are not counted in because they are multiplied by a 0. Okay, so this is called the I and J moment of an image, a binary image. Now, if you set both I and J to 0, it's simply going to be summation of I. And so it's basically what? Summation of all of the pixels for which I equals 1, and that is the area. So the area is moment 0, 0 of an image. And it's not really hard to do. All you need is to use the command find. So you say, hey, find this I for me. And it does. It gives you all the locations that the image is not equal to 0. And if you apply the command sum to it, so let's say this find gives you 60 pixels for which I is not 0. Correct? If you sum it, or say what? Find I, length of it. You don't need sum because find gives you location. You need length. I'm sorry. You need the length of this. If this find is an array of 60 linear indices for the locations that the value is not equal to 0 or is 1, the length of that can easily give you A. Okay, so it's not really hard to find A. It can give you perimeter, which involves a little bit more math. So here you have to track of the boundary. And again, it gives you this perimeter in terms of number of pixels. Okay, so it says the edge of this object, the perimeter, has, let's say, what, 200 pixels and so on. And you can definitely get this perimeter from this here, this guy. This skin image can definitely give you the perimeter, right? If you just count that. You also have the bounding box and convex hull, which are the smallest. Bounding box is the smallest rectangle. Convex hull is the smallest polygon in general that can contain your blob. So your blob will be entirely inside this rectangle or polygon. Then we call it the bounding box, or we call it the convex hull. So these will give you the coordinates of the vertices. Okay, when you run it with bounding box or convex hull, it gives you these. For convex hull, it gives you the coordinate. For bounding box, it typically gives you the top left coordinate plus the width and the height. It doesn't give you 4 coordinates. It gives you this location plus this W and H. It can also give you the centroid of the blob. How do you find centroid? Well, if you remember from your statics, hopefully, then the centroid of an area in general, if you have X and Y coordinates, the centroid of an area was what? If I say what is x bar here, you said it's the integral of x dA over integral of dA or a. So this is called the first moment with respect to the y-axis. And here, that's the same thing. If you keep this power j to 0 and keep power I to 1, this m10 will be an approximation of this. Or the equivalent of that, really, not approximation, digitized version of that, let's say. Why did I say approximation? Because now you have to break this area into what? Into pixels. And some of these pixels go beyond the boundary, some of them go above the boundary, and so on. But you digitized it, basically. And if you divide it by a, which is m00, so this guy was m10, the division of these will give you x bar. Similarly, y bar, which was integral of y dA over a, integral of y dA will be to make I0 and j equal to 1. So it's going to be m01 divided by m00. That's what? That's y bar. Okay, so if you calculate these two moments, m10 and 01, and divide them by the area, that's what? That is the location of the centroid, and for these to be calculated, you need a double summation, right? One that goes over rows of the image, one that goes over columns of the image, and you can easily calculate both of these and get the centroid, which you can see here. For that blob, which had that extra tail for this one, if I do a bounding box, clearly because of this tail, the bounding box could be a little bit larger, and the centroid of it is somewhere there, which you can see in this picture. Right? And let me first show you those, and then we talk about circularity, orientation, and eccentricity. But the command to use is called stat equal region props of binary image and properties. So here, if I go to measurements, so here I choose blob number 1. I say my binary image equals where L was double equal 1. Choose blob 1. Get me all the stats that I want. And then, as I said, this stat is a structure. So I have to use dot operator to access its centroid. And then centroid 1 is Cx, centroid 2 is Cy. Right? And then I can get the bounding box or anything else. So let me show you here. If I run this for you, this is the stat. It's a structure. So if I say stat dot area, you clearly see that it has 1677 pixels. This is the centroid of it, and this is the bounding box, which, as I said, this is the top left corner, and this is the height and this is the width and the height of that bounding box here. That you see here, I have superimposed on the image. So I showed the blob 1 at Cx and Cy. I added a red star, and then I used the command rectangle and pass to it the information, which is top left corner, width and height, and say with red color line width to add that rectangle. Okay, so if I run this whole thing together for you, there we go. Right? This is the bounding box. You see every white pixel falls inside it, and this is the centroid of that blob. So now if the blob moves, because it belongs to a moving object and you can detect it consistently, you can also look at the centroid of the blob as the person moves. Okay, so this is good for object tracking and where the object is at any time point. Put a window around it and find the centroid of it. Good. So let's go back. Okay, so in addition to the area, perimeter, bounding box, or convex hull and centroid, is there anything else we can get from this region props command? Yes. There are several things, but some of the important ones are circularity, orientation and length of major and minor axis, and the eccentricity. So what are they? What is circularity? So in circularity, you measure two entities, mu and sigma, which are the average and the standard deviation of the distance between the center of a blob and the pixels on the circumference, on the basically the edge. And you look at the average and you look at the standard deviation and you divide, that ratio is circularity. Now, what kind of numbers should I expect for this? Well, if the blob is perfectly circular like this, right? Then R bar and C bar, that's here, the centroid. You have some pixel here on the edge. You calculate the Euclidean distance, and the average of those is mu, and the standard deviation of those is sigma. So if it's perfectly circular, then all of these numbers that you measure here, all of them, are going to be all equal to the radius of the circle. So every single one of these norms is simply going to be what? R, 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 R. So this mu is also going to be R. What about sigma? So in sigma, you subtract each distance from R, which should be 0. And so sigma is going to be 0. If they are all R, they are all the same, there is no variation, then the standard deviation is 0. So here you are dividing R by 0, which makes this number go to infinity. So if it's perfectly circular, it's going to be a very, very large number, potentially infinite, if it's a perfect circle. But if it's what? If it's not like a circle, something like this, or if it's, let's say, an ellipse or something, here these distances clearly vary, and they have some big variation, right? From this big number to that small number. The average still is some medium number, but the standard deviation gets bigger and bigger. So the more it deviates from the circle, this average might or might not go up, but sigma definitely goes up, which means circularity goes down. So the bigger the number you get from this measure, the closer it is to a circle. The smaller it gets, the closer it is actually to kind of like a very, very long ellipse, which becomes close to a line. So when it gets almost close to a line, now some of your distances are very long, some of your distances are extremely small, so your sigma is very large, your circularity measure is the smallest it could be. If it's an infinite line, then circularity measure goes to 0. So this is how MATLAB calculates circularity. You can also calculate the orientation, angle theta, as well as the length of the minor and major axis. Well, how would you do that? Well, let's say the blob that you have is like an ellipse, for example. This is the simplest shape. How do I find the angle between the major axis here and the x-axis, this angle theta? And then how do I find the major axis length, which is this one, and minor axis length, which is this one? Well, the first thing is, if I give you this blob, right, how can you get me the angle between the major axis and, let's say, the x-axis. How do you find this angle theta? And for that, what we need is now we have to calculate what we call central moments. The difference between central moment mu and regular moments mij is, in mij, you are raising the location x and y to the powers I and j and multiply by the intensity. Here, you first subtract the location of the pixel from the centroid, then raise it to the powers p and q or I and j, and then you multiply by the light intensity. So this f is the same as I. And p and q are the same as small I and j that you see in that formula. So the only difference is the distances are here from centroid raised to the power. And what's the major difference between central moments and regular moments? Well, central moments are what we call shift invariant. Or you might, instead of shift, call them translation invariant. What's good about them? The good thing is, if I calculate the central moment for an ellipse that is here, or if I move it to here, the result is going to be the same. But if I calculate the regular moments, they are not. So here, this m10 of this object and m10 of this one, they are definitely not the same. But if I calculate mu10 for this object and mu10 for this one, they are the same. Because the location of the pixels x and y that you have for each pixel in it or outside it, if you just directly raise them to a power, you would get different numbers. Just consider this one, look at the y of it and look at the x of it, and compare it against this one. Clearly, when you raise this x and y to the same power and multiply, you get different numbers. But if you subtract them from the centroid and raise to the power, the position of those points with respect to the centroid give you the same distance in both shapes. So the result is going to be the same. So that's one of the good things about central moments. They are shift invariant. So here we calculate three central moments: mu20, mu02, and mu11. We calculate three moments, central moments. And if I divide these three moments by mu00, what is mu00? Well, when you make this power 0, again, you're adding all the light intensities together. So mu00 is the same as m00. Let me write m. And that is the same as a. So the central moment 0, is the same as the area of the shape. Now, if you divide these three mu's, 2, 0, 0, 2, and 1, 1, by 0, 0, and call them mu2 prime 0, mu02 prime, and mu11 prime, then based on these three entities, I can, using an arctangent, calculate the angle of what? The angle of the major axis from the x-axis, theta. And this is exactly similar to, if you remember from your statics, the principal moments, right? And the principal axis. This is exactly the same formula, principal axis. So this theta give you the angle of the first principal axis, which is the major axis. Okay, that's the exact same thing. So you calculate angle theta, that gives you the orientation. Once you have the orientation, then what? And you also have the centroid. Remember, I can calculate the centroid. And I can calculate what? I can calculate the angle theta. So you know in this direction, you should have major axis. You know this is the centroid. Now calculating this length is not such a big deal. Or perpendicular to that 90 degrees plus theta. So this angle, if it's theta for major axis, for minor axis, right, or the second principal axis, this angle here is going to be theta plus 90 degrees. Then calculating this distance here is not going to be a very hard thing. Okay, so calculating the length of major and minor axis once you have the centroid and the angle theta is not necessarily a hard job. It's just finding the Euclidean distance between a few points, right? Either this one and this one, or this one and this one. Okay, so that's how you get these guys. Finally, you have eccentricity, which is the ratio of the distance between the focal points and the major axis. So if you have this ellipse again, and this is the major axis, and the focal points are here and here, this distance, if you find this distance between the two focal points and divide it by the total, what? Major axis length, that should give you here. You call it 2c, and you call this whole distance 2a. This ratio is simply c over a, or 2c over 2a. Okay? Now, you know, if the length of the minor axis is 2b, you know there is a relation between A, B, and C, right? Semi-minor A, major A, semi-minor B, and the length from center to the focal axis C. Between A, B, and C, there is a relation. And that is B squared plus C squared equals A squared. So when this ratio gets bigger, this E eccentricity gets bigger, means C is closer to A. That means B goes to 0. That means your ellipse becomes very, very narrow like that. And when what? When C goes to 0, B goes to A, or E goes to 0. B goes to A, and you get what? You get a circle. So for a circle, this ratio is 1. This ratio is 0 for a circle. For an ellipse that is getting almost close to a line, very, very extremely narrow, this becomes 1. So this E is between 0 and 1, and the bigger it is means the narrower and the more elongated the ellipse becomes. And that, of course, you can easily get from the length of the major and minor axis. If this is 2A and this is 2B, from here you can calculate C and plug it into your eccentricity. So you see all of this coming from math, and we can perform all of these calculations. All we need to pass to the command region props is the property that you want. If you don't pass a property to it, like here, if you remember, the only thing this one will give you are 3 of the properties: bounding box, centroid, area. But if I say, hey, give me the eccentricity of this region, right, or the circularity or whatever property that I want, then you see that gives you the number. You see here the circularity is what? Is a small number, and if you remember, small number means sigma is large. And sigma large means it's not really so circular. When it's very large, that's circular, and clearly the shape of this region was not anything circular. Just look at it, right? Especially because of this tail. Okay? Or if you want the eccentricity, again, you just pass the eccentricity. You see, 0.6, which is somewhere between a very narrow ellipse and a circle. Okay, so you can measure any of those properties if you just pass it to this command. Okay, so hopefully that was clear to you. Now, the final thing that I want to talk about are invariant moments. And they are first time described by a scientist named Hu in 1956 or something, so many years ago. And he found 7 moments for a binary image, that these 7 moments have several invariant properties. What are they? Well, if you remember, I just told you that the central moments, mu's, they have an amazing property, these mu's that here we described, right, these guys, they are shift invariant. So if I calculate these guys for a blob, wherever that blob is in the image, as long as it's the same blob, just shift it from one place to another, the result is going to be what? The same. Great. That makes our recognition jobs a lot easier later when we do object recognition or blob recognition. So if I have a blob, let me show you. Let's see. Read an image, and then here we go. So here I have 4 shapes. 2 of them are square, but the squares are in different sides, locations of the image. Their size are different and their orientation are different. The same thing with the ellipses. The orientation different, the scale is different, the location is different. So if I want to say between these 4 shapes which pair are the closest to each other, I have to say shapes 2 and 3 are the same shape really, and 1 and 4 are the same shape. They are square or they are ellipse. But if I just want to go with the mu alone, that is not going to give me good numbers that I can use for comparison. Because yes, mu of the square, this square and this square, they can have the same mu as long as it was just the centroid went from this location to here, but not rotated, not scaled. When you have a bigger object, it has more pixels that will contribute to mu, so it definitely has bigger mu's compared to the same shape but smaller. So mu's are not scale invariant. Bigger shapes typically have bigger mu's than smaller shapes, even though they look alike. And they are also not the same for rotation. If you rotate an object and still keep even the size of it constant, the mu is going to change. So can I do something on these mu's to make them both scale invariant and what? Rotation invariant? And the answer is yes. And that's what Mr. Hu found first time. He said the first thing you do, you divide each and every one of these mu's by mu 0, 0. Remember, mu 0, 0 was the area, to the power 1 plus I plus j over 2. If you normalize each one of these central mu's by mu naught to this power, then the resulting moments eta, they are also scale invariant. So now if you compare eta against eta, not only they are shift invariant, they are also scale invariant, yet not rotation invariant. If you want to make them rotation invariant, you have to combine these etas according to these formulas that you see, like add eta to 0 and 0, 2. That guy is going to be constant regardless of how much you rotate the blob. The same thing here. This entity is going to be the same regardless of what you do to the blob. That entity is going to stay the same and all the way. So he says these 7 moments are also rotation invariant. So now if I calculate these who invariant moment, these 7 guys, for these 4 shapes, they should give me similar numbers for shape 1 and 4, and then similar numbers for what? Shape 2 and 3. So just by comparing the distance between the who moments of 1 and 4 and 2 and 3, I should say which 2 shapes belong to the same class, to the same category. So you see here, my goal is what? Object recognition or classification. If I see a figure of some object in image 1, and in image 2 that object moved somewhere else, rotated, or taken at a longer distance or a shorter range, I could still say, hey, if that was a square over there, that's still the same square over here, but taken at a different angle, at a different range, and at a different pan and tilt angle. Okay, so none of those should affect my judgment of what shape it belongs to. And here in my code, I calculate these moments using a utility function, which I wrote here, who moments. So I calculate the x bar and y bar that I need for my mu's. I calculate my area. I calculate my you see here another simpler way that you can get the area. Remember, I told you last time using length and find. A simpler way to do it is just to sum all of the pixels in that blob. Just sum it up. Convert your matrix into a vector and sum it up. Well, all the ones will be added. The zeros have no effect, so this is going to be sum of all the ones. So this is another way to get what? The area of a blob in pixels. And then here I calculate my M1001 to get my X bar, Y bar. Here, these are those pairs that I have for the who moments. If you see, the moments are 2, 0, 0, 2, 1, 1, 3, 0, and so on, right? Just look at these indices, right? The subscripts that you see. So there are 7 of them that I provided in my code. And first I calculate my etas, right? So I calculate my mu's in the inner loops. Then I calculate my etas by dividing by that mu 0 to that power, 1 plus I plus j over 2. And then I calculate my i's and I return them. So when I upload this code for you to work with, I also upload for you this utility function. And here you see, calculate for you the set of moments for shape 1, for shape 2, 3, and 4. Okay, so if I run this section for you, not only you see which shape is which, you also can see those set of moments. So look at them. For shape 1, 5 of these moments are almost 0. There are 2 moments. This one is not really 0, only the first 4 decimals are 0. If you use long format, right? Let me do long format and run this section one more time. The second one is not exactly 0. Let me run it one more time for you here. Okay, so here. Okay, you see this number is not 0, but up to 4 decimal it is. But for shape 1, it's 16.6 and some small number at moment 2. The rest of them are 0 for shape 1. Now, which shape was close to shape 1? Shape what? 4. Look at shape 4. For shape 4, look, 16.68 and again what? Almost 0. Now, these numbers are not perfectly 0. For this one, they are, but they are very small. You see? They are up to 6 or 7 decimals or more than decimal 0. So these are practically close to 0. Even this number we can say is almost 0. So the only real non-zero number you have for shape 4 is 16.68, and for shape 1 is what? 16.67. So you see shape 1 and shape 2 are showing very, very similar what? Sets of moments. But for 2 and 3, which are the same, look at the numbers. The first moment is 0.18. And the second one, that is, you can say it's maybe meaningful. This is 0.07, this is 0.09. The rest of them are almost 0. So you see, clearly these two belong to the same category. If you look at them, 18, 0.18 and 0.18, then 0.7 and 0.9, or 0.8 and 0.9. Right? But the scale of this 0.18 is completely different from this one and this one. Right? So if I want to take a Euclidean distance between these 4 shapes and cluster them into 2 clusters, clearly data number 1 and data number 4 are the same shape. Data number what? 2 and 3 are the same shape. Okay, so that's how you can use these invariant moments to do a classification or basically object recognition for a binary image. For images that are grayscale, they are not as useful. Plus, even for binary images, as you can see, many of these moments are literally insignificant. So who invariant moments are not the best set of moments that are out there? If you're looking for something scale invariant, shift invariant, and rotation invariant, but they are the start point, okay? We talk about better, more robust features in an image for object recognition and detection, like surf and so on. But those are advanced lectures that we'll see in a few months from now. So I just wanted you to know about this important topic of who invariant moments. So hopefully this long lecture on morphological operators was useful to you. As I said, I'm going to upload both of these code for you, and hopefully you find the lecture useful. Thank you. See you in my next video.